After studying this module, you shall be able to know what are SEi mechanisms, that is substitution, electrophilic, internal mechanisms. You will learn how SEi mechanisms operate. You will be able to identify substrates, leaving groups and solvent conditions that promote SEi mechanism. You will be able to evaluate the stereochemistry of SEi and SEi- mechanism. You will be able to analyze the importance of internal assistance in substitution reactions. Electrophilic substitution reactions at the saturated carbon atom are classified based on molecularity of reactions and stereochemistry of products formed. There are 4 major classes of electrophilic aliphatic substitution mechanisms. First, unimolecular SEi mechanism, which is a 2-step process. The other is bimolecular Se2 front, Se2 back, and substitution electrophilic internal SEi, which are single step mechanisms. In SEi mechanism, the electrophiles with suitably placed functional groups attack the sp3 hybridized substrate from the front, whereby a portion of the electrophile might assist in the removal of the leaving group. It is a concerted mechanism leading to retention of configuration at the reaction center. A simple schematic is shown here. RMXN reacts with En to form a 4-membered transition state, giving Re as the product. Here R can be methyl, ethyl or any alkyl group. M is a metal atom. En represents electrophile with suitably placed nucleophilic site. The SEi mechanism involves second order kinetics, first order in substrate and first order in the electrophile. The internal assistance provided by the electrophile locks backside attack of the electrophile. Thus, wherever second order mechanism involves internal assistance, backside attack of electrophile is impossible. As a result, similar to SEi front mechanism, SEi reactions proceed with retention of configuration. The SEi mechanism has also been called the SF2, the Se2 closed and the Se2 cyclic mechanism. SEi mechanism reactions are not limited to 4-membered cyclic transition state, but a 6-membered or 8-membered transition state might as well are possible. For instance, the reaction of symmetrical dialkyl mercury compound with acetic acid proceeds through a 6-membered cyclic state. Dibutyl mercury with acetic acid reacts to form a transition state which is 6-membered cyclic transition state to give butane. This reaction proceeds with retention of configuration. Further, on the basis of evidence from reactivity studies, a stepwise mechanism called SEi coordination mechanism had been suggested for situations where the reactant En first coordinates with the metal atom in the substrate. In the second step, actual electrophilic substitution takes place when the complex is decomposed to the product as shown. RMXN reacts with En to form a complex which decomposes to give Re. This process has been called the SEC or Se2 coordinate mechanism. Such mechanisms also proceed with retention of configuration. These are bimolecular but may follow complex kinetics, as at least 3 elementary steps are involved in the reaction. Another situation in bimolecular electrophilic substitution may arise where an assisting nucleophile B is present during the reaction. The additional nucleophile can modify the course of SEi mechanism by either getting incorporated in the substrate as shown in case 1 or may become a part of the reagent as in the case of 2. In case 1, RMXN reacts with B to form RMBXN. This RMBX further reacts with the electrophile En to form Re. In second case, En electrophile first reacts with the base to form an intermediate EBN complex. This reacts with RMXN to form the product Re. Experimentally, case 2 has been found to be operative for SEi mechanism as it favors the cyclic transition state. Distinction between Se2 front and SEi mechanism we will study now. Both Se2 front and SEi are bimolecular substitution reactions that proceed with retention of configuration. Therefore, mechanistically, it is difficult to assign a particular mechanism to a specific reaction. Ingold et al. Applied ingenious tools to distinguish between the two mechanisms based on the reagent structure of alkyl mercury complexes and based on effect of salt on rate of reaction. Both the factors help to distinguish which mechanism is in force for a reaction under a fixed set of conditions. First, reagent structure, then we will see the effect of ionic strength. Reagent structure for Se2 mechanism, a relatively more electrophilic cationic mercury complex such as HgBr2 is desirable, whereas for SEi mechanism, a weakly ionic reagent such as LiHgBr3 is more suitable. The rationale being the extra bromide ion in LiHgBr3 would decrease the ionic character of transition state and acts as an assisting nucleophile for SEi mechanism. Experimentally, it was confirmed that with the LiHgBr3 reagent, there was no retardation in the rate of SEi reaction, whereas rate of Se2 mechanism was retarded by this reagent. Secondly, we will study the effect of ionic strength, how it affects SEi and Se2 mechanisms. The effect of ionic strength of salt on the rate of reaction was studied. It is known that for a reaction in which the reactants are neutral and the transition state is more charged, such reactions are aided by an increasing concentration of added ions. Experimentally, the salts of increasing ionicity such as HgBr2, HgOAc whole twice mercury acetate, HgNO3 whole twice mercuric nitrate were investigated. With increasing ionicity of mercuric ion Hg2+ would predominate upon dissociation. Since SEi mechanism requires assistance from attached ligand to maintain the cyclic transition state, the presence of free Hg2+ ions would not favor SEi mechanism, but would enhance rate of Se2 mechanism. The reaction of these three salts with di-S-butyl mercury in ethanol were studied. The results showed absolute rates increase strongly with increasing ionicity along the series mercuric bromide, mercuric acetate and mercuric nitrate, thus indicating Se2 mechanism being operative for the reaction. This is because the SEi mechanism do not involve charged intermediates, therefore added salt would have less effect on the reaction rate than for the relatively more charged transition state of Se2 front mechanism. Now let us study the factors affecting SEi mechanism. There are many factors that influence rate and mechanism of SEi reaction. The most important factors being nature of substrate, nature of reagent, role of solvent. We will study these factors one by one in detail. Firstly, nature of substrate, how the nature of substrate affects SEi mechanism. For SEi mechanism, varying effect of substrate structure have been observed. Similar to Se2 front mechanism, the branching at alpha carbon increased rate of reaction due to electron donating inductive effect of R groups that stabilize the electron deficient transition state. However, beta branching decreases the rate of reaction significantly, showing effect of steric course on reaction. This order of substrate structure, polar and steric effect on reactivity is operating in non-polar solvents. Thus, the order being methyl least reactive, then ethyl, propyl and isopropyl most branch will be the most reactive amongst these. Another factor is the nature of reagent. As discussed, less ionic reagent such as lithium HgBr3 with suitably placed nucleophilic groups in the reagent favor SEi mechanism is compared to ionic reagent HgBr2. Role of solvent. Role of solvent nucleophilicity has been shown to play a decisive role in fate of a bimolecular reaction. If the solvent has only little nucleophilic character, then the electrophile with suitably placed assisting functionality may predominantly assist the reaction, turning the reaction in favor of SEi mechanism. However, when a bimolecular reaction takes place in a polar nucleophilic solvent, then coordination of solvent to the metal atom in the transition state would lead to Se2 mechanism. Thus, SEi will be favored in non-polar solvents and mechanism Se2 in polar solvent. The relative rates of electrophilic substitution of metal alkyls of type R and M, where R varies through methyl, ethyl, propyl and isopropyl, two sequences of reactivity can be distinguished, and that these two sequences are solvent dependent. They are first a steric sequence methyl, ethyl, propyl, isopropyl observable in polar solvents where the Se2 mechanism is operative, and second is a sequence showing an increasing contribution of polar inductive effects methyl much less than ethyl, ethyl greater than propyl and isopropyl much greater than propyl, observable in non-polar solvents where the SEi mechanism occurs. Now, we will study some examples of reaction with SEi mechanism. First, let us see SEi- mechanism with rearrangements. Allylic organometallic compounds may undergo electrophilic substitution internal reaction at the alpha or gamma carbon atom. If the attack is on the gamma carbon atom, then the reaction is called SEi-, that is bimolecular electrophilic substitution internal reaction with rearrangement. This is an example of rearrangement. CH3CH double bond CH CH2 reacts with En to form CH3CHE CH double bond CH2. Most electrophilic allylic rearrangement involves loss of hydrogen, but they have also been observed with metallic leaving groups. The crotyl mercuric bromide reacted with HCl 10 to the power 7 times faster than N-butyl mercuric bromide, and the product was 1-butene greater than 99% yield. This reaction thus fits SEi mechanism as seen here. Next is SEi mechanism with the assistance from external nucleophiles. The complexes of bromine with ethers R2O-Br2 were found to be more effective reagents in SEi reactions with organomercury compounds rather than with free bromine. This is because in the complex R2O-Br2, the electron density at one of the bromine atom is higher than on the other bromine atom in the Br2 molecule. Therefore, alkyl mercury compounds reacts with bromine ether complex where close to neutral oxygen carries partial positive charge and the other bromine a partial negative charge. Thus, it is polarized in carbon tetrachloride, reacts to form a 4-member transition state which decomposes to give alkyl bromide. Another example of solvent assistance is the proteolysis of organomercury compounds by hydrogen chloride, where the rate of reaction was found to decrease on raising the concentration of water in the solvent. This showed that the reactant was not the solvated proton but the ion pair of molecular form of HCl. RHGX reacts with HCl to form a 4-member transition state to give RH. The nucleophilic coordination of chlorine with mercury was proposed to occur in the pre-kinetic stage, followed by electrophilic of attack of hydrogen on carbon atom through a cyclic transition state to complete the reaction. Now, another example is the Metallo demethylation reactions. The metal exchange reactions are equilibrium reactions that are useful only if the equilibrium lies in the direction of desired product. Generally, the equilibrium is observed to lie in the direction in which the more electropositive metal is bonded to that alkyl or aryl group, that is the more stable carbon ion. Rm reacts with R-M- in equilibrium with Rm- and R-M. As examples, preparation of vinyl lithium from phenyl lithium and tetravinyl tin and the formation of dialkyl amino organolithium compounds from the corresponding organotin compounds include a SEi mechanism. RR-NCH2 SnBu3 reacts with butyl lithium at low temperature 0 degrees Celsius to form RR-NCH2 Li along with tetrabutyl tin. This is a good method to prepare organolithium compounds, as lithium compounds are not prepared easily by other ways. The SEi mechanism is useful for formation of higher order cuprates starting with a vinylic tin compound. SnR-3 reacts with Me2CuCnLi2 to form RCuMeCnLi2, where R is a vinylic group. These molecules are too unstable to be isolated but are used directly in situ for conjugate addition reactions. Another reaction for formation of such complexes with zinc metal is reaction of RCHOAC-Br in presence of zinc dust, THF, dimethyl sulfoxide and copper cyanide to give RCHOAC-CuCnZnBr. Some other miscellaneous reactions involving SEi mechanism are iodination of alkyl mercury iodide in presence of cadmium iodide follows cyclic transition state mechanism even in polar solvents such as dimethylformamide, methanol, ethanol and 70% aqueous dioxane. So, RHGI reacts with I2CD I2 to to form again a 4-member transition state to give RiHDI2 and cadmium iodide. Set of reaction with different X groups were carried out and the effect of substituent Y on the mechanism was deciphered. Here X can be bromide HgBr3-. In this reaction, structure of the transition state were found to be very different for different Y groups. This was confirmed by the different influence of the substituent Y in the para position of the benzene ring of the organomercury substrate. So, one of the transition state is shown here. Thus, the reaction of mercurated ester with C6H5 whole thrice CBr H3Br2 was found to be accelerated by electron donating groups and retarded by electron withdrawing groups in the following order: C3H7, then C2H5 much greater than C4H9, much greater than hydrogen, then fluoro, chloro, bromo, iodo, and least is nitro. Overall, it was found that the substituent influences rate of reaction based on their polar and steric influences. In another reaction, the reaction of endoisomers of the 2-nor-bornyl Grignard reagent with HgBr2 to give 2-nor-bornyl mercuric bromide has been shown to proceed with retention of configuration. For the reaction, SEi and Se2 type mechanisms were proposed to be plausible. However, due to Lewis acid nature of magnesium 2, the SEi process were proposed to be the predominant mechanism. So, nor-bornyl magnesium bromide, which is 95 to 100% endoform, reacts with mercuric bromide to give 94% endoform and with carbon dioxide to form a carboxylic derivative in again 95% endoform. The reactions were proposed to proceed through the 4-member cyclic transition state as shown here. Disproportionation reaction of organosilanes proceed in organic solvents such as benzene via the following transition state. Me3SiR reacts with aluminum bromide to give Me4Si. The reaction of dibenzyl mercury with trifluoromethyl mercury salts and of tetramethyl tin with trichloromethyl tin follow SEi mechanism in non-polar solvent. So, BZ2Hg benzyl mercury reacts with CF3HgX HgX2 to give benzyl HgCF3. Tetraalkyl tin reacts with RSNX3 to form R2SNX. Now, let us summarize what we have studied till now. Substitution reaction, electrophilic internal SEi are substitution reactions where a suitably placed portion of the reagent assists in the removal of leaving group, providing internal assistance. SEi mechanism follows second order kinetics and proceeds with retention of stereochemistry. SEi mechanism proceeds via a cyclic transition state. SEi and Se2 front mechanism can be distinguished based on nature of reagent and salt effect on rate of reaction. The transition state for Se2 front is more ionic than transition state for SEi. Therefore, Se2 front reaction are more affected by polar solvents and ionic strength of reagents. Alternate pathways for SEi mechanism have been proposed, whereby first electrophile coordinates with the metal atom followed by actual electrophilic substitution. In non-polar solvents, the inductive effect decide reactivity of SEi mechanism as follows: methyl least, then ethyl greater than that, propyl less than ethyl, and isopropyl maximum.